Good evening in New York. Are you hearing me okay? You just wave and let me know.
Yes, we hear you.
Okay, great. So Ted did finish grading homeworks 3 and 4, and they're being mailed back to you guys in New York. I have them here for Pittsburgh students tonight. So those of you who are here, we'll start passing them out and hope to lighten my load a little bit. Lecture 7. We'll wait just a little bit. It's not 5:30 yet. So it's good that this class is coming to an end. The weather is getting entirely too nice to be inside. Even I'm having trouble preparing lectures. Well, the clock on the wall says it's 5:30. We have a couple of things to do tonight. So 2 new topics that will not be on the final exam because they're coming right at the end and we don't have time to practice with homeworks. One of them is I'd like to talk about American options and the whole early exercise business because you need to know that even though we're not going to have an exam question about it. And the other is the reflection principle, which you're probably already using in the Monte Carlo course, but I'd like to develop it a little bit more systematically. Sometimes you get questions on job interviews that require you to use some reflection principle arguments. So we have those 2 topics to cover. And then there was a discussion that got started this week on Blackboard about self-financing portfolios. And so I'd like to start this evening and talk a little bit about that. The idea behind self-financing we addressed, and you could see something about that on the final exam, and because it's fairly important and a little bit complicated, I'd like to go back and do it a little more systematically and carefully than we did it in class. And finally, this is the evening when we're supposed to do the course evaluations. Tepper is set up so that you have to evaluate me before I evaluate you. So it's not my rule, it's just the way it's set up. We'll take, during the first break, we'll take a little bit longer time. I'll return homeworks here in Pittsburgh, and we'll do the course evaluations as well. So I hope you brought your laptops with you. And I think you already have gotten an email that tells you where you go in order to do that. So my first topic of the evening, unless there's a question before we get started, is the notion of self-financing portfolios. Oh, and I'll remind you that Friday afternoon I'll be here in 1:45 from 1 o'clock till we get tired, or 5 o'clock, whichever comes first. And we will be connected to you guys in New York, and it will be recorded. It's just free for all. Sort of stump the instructor, see if you can ask me a question that I don't know the answer to, pertaining to stochastic calculus, of course. And if you don't come with questions, I will pick out some of the review problems that I posted and talk about those. Okay, so self-finance. Any question about anything before we get underway? The idea of self-financing portfolios is the following, that we often have two assets. We could have more, but let's take the case of two assets. So these are asset prices. And then we have positions of assets, delta 1 of t and delta 2 of t, delta. So these are positions in the assets. Let's spell positions correctly. And then we have portfolio value, x of t, which is the number of shares of asset 1 we own times the price of asset 1 per share, plus the number of shares of asset 2 we own times the price of asset 2 per share. So this is the portfolio value. Let me call it equation 1. And then we ask, if this is our portfolio value and we move forward in time and we're going to change our positions, delta 1 of t and delta 2 of t, will that finance itself? That is, when I'm going to change my position, will it be that I'm increasing my holdings in stock 1 and selling off some stock 2 to finance that, or am I going to have to put money in? And the condition that says that the portfolio is self-financing is that if you take the differential, you get delta 1 of t ds1 of t plus delta 2 of t ds2 of t. So this is the self-financing condition. And of course, if you take the differential honestly using Ito's formula, that's not what you get. If you take the differential honestly, you get 4 more terms. You will get, in addition to this, you will get an S1 of t d delta 1 of t and a ds1 of t d delta 1 of t, and you will get an S2 of t d delta 2 of t and a ds2 of t d delta 2 of t. And so what equation 2 is saying is that these terms add up to 0. And this is the financing condition. And we talked about that once in discrete time, but let me take just a moment and do it again. Because if you write down the discrete time analog of this, then I think you agree that the thing in the box being 0 is exactly the self-financing condition. And so the way it would work in discrete time is we'd have a time tk, and we'd take our positions, delta 1 of tk and delta 2 of tk. And then we would hold those positions out to time tk plus 1. And then once we got to tk plus 1, we'd rebalance. We'd move to the new positions, delta 1 of tk plus 1 and delta 1 of 2 of tk plus 1. And if I write this condition in discrete time, what I have here is S1 of tk. Let me factor the d delta 1 out and write these two terms first. S1 of tk and ds1 would be S1 of tk plus 1 minus S1 of tk. And those are both multiplied by d delta 1. And in discrete time, that would be delta of tk plus 1, delta 1 of tk plus 1, minus delta 1 of tk. And then here I have an S2 multiplying a d delta 2. Here I have a ds2 multiplying d delta 2. I will factor the d delta 2 out and write S2 of tk plus S2 of tk plus 1 minus S2 of tk multiplying the d delta term, which in discrete time would be delta 2 of tk plus 1 minus delta 2 of tk. And of course, these two can't. And so what I have here is S1 of tk plus 1 times the change in delta 1 plus S2 of tk plus 1. I don't need that parenthesis. Times the change in delta 2. And the self-financing condition is that this thing in the box is a 0. And what it says is that when you get to time tk plus 1, and you're now going to change your positions, the prices of the assets are now S1 of tk plus 1 and S2 of tk plus 1. And then you multiply those prices by the change that you make in your positions. And these two, one should be positive and one should be negative, and they should add up to 0, which means you're selling something in order to buy the other, and it's financing itself. So often when the self-financing condition is written down, you see it written the way that I've written it here as two equations. One of them tells me the value in my portfolio, and the other one tells me the differential of the portfolio. And the change in the portfolio value is solely due to change in the asset prices, S1 and S2, and not due to any change in the positions. And so you get only the first two terms in the dx. There's another way the self-financing condition gets written, and that's by taking equation 1 and solving it for delta 2. And so equation 1, if I put it here where you can see it in New York. So equation 1, if I solve it for delta 2, it says that delta 2 of t is equal to x of t minus delta 1 of t, S1 of t, over S2 of t, and substitute that into equation 2. And if you do that 3, it says that dx of t is equal to delta 1 of t ds1 of t plus x of t minus delta 1 of t s1 of t over s2 of t ds2 of t. And if you start with equation 3, you have only one equation to worry about. What equation 3 is telling you is that you only get to choose one position. You get to choose delta 1, and once it's chosen, the game is over, because delta 2 is now determined by the self-financing condition. And so you have a choice. You can either write equations 1 and 2, or you can write equation 3, and then, of course, the delta 2 would have to be given by this, and you could go back to equations 1 and 2. We have normally been writing it in the form of equation 3. And in particular, the example that we've seen most often is when the second asset is a money market account. So if the interest rate is a random process, then that's e to the integral of the random process. Of course, if the interest rate is a constant, then this would just be e to the constant r times t. And then ds2 of t When you differentiate that, you'll always get the exponential back again, and then the derivative of the integral is going to be r of t. So the difference of that is r of t, s2 of t dt, and equation 3 becomes dx of t is equal to delta 1 of t ds1 of t. The ds2 over s2 is r of t dt, and so I'll put the r of t here. And I'll put the dt here. So we've been using this equation all along, and as long as we start with this equation, the self-financing condition is already automatically taken care of. It's only when we start with equation 1 that then we have to write down below it equation 2, because equation 1 doesn't imply equation 2. Equation 1 implies that the differential of x has 6 terms, and you have to put in the extra condition that 4 of them add up to 0.
How did we actually end up in the self-financing condition for the continuous case? In the discrete case, it's kind of very much intuitive as to how we could easily bring it up. Like, how did we conclude that those 4 had to add up to 0?
There's a paper by Duffy and Prodder which takes the discrete case and passes to the limit and shows you that what I've written down here in the limit, it seems intuitively right, but you can actually do a mathematical proof that this limit is the limit, that this formula, or I guess that this actually proves that this is the limit of this. So there is a mathematical proof that we're not doing, because I think it's sort of intuitive, and we don't want to spend our time bogged down in that. But you're quite right. I mean, it's something has to be proved here. All right, so with that introduction, let me remind you of how we did the Black-Scholes replication. We're doing Black-Scholes. The first asset was a stock. We had a constant interest rate, and the stock had a constant volatility, sigma 1. And the second asset was a money market with a constant interest rate. Second asset starts at 1. So what I'm saying here is just that the second asset is like this, except the process r of t here is just a constant, little r. And we showed that if you take x of 0 to be the price of a call, and the C function here, C is given by the Black-Scholes formula. And if you take the delta 1 of t to be the delta of the call at each time t, then x of t and the call price will be the same. Okay, so that's a classic argument. That should have been in stochastic calculus 1. What you did here was you started with this model for the evolution of x, except that you had a constant interest rate r. You computed discounted x. Then you computed the discounted differential of c. I don't know what this 2 is doing here. Computed the discounted differential of c. You equated the 2. And then you said if they start the same, they'll have to be the same at all times. Now, we didn't bother to do the checking, but it would be true in this case that there's a self-financing condition here, and it's being satisfied. And what does the self-financing condition say? Well, it says there are actually 2 positions you're taking. You're taking this position in the stock. You're also taking a position in the money market account. And the position in the money market account, delta 2 of t, is given by the formula at the top. You take your cash and you divide it by the price of the money market account to get how many shares of money market accounts you own. And so it's x of t minus delta 1 of t s1 of t. And the price of the money market account, in the case of a constant interest rate, is that. And so we would normally write that as e to the minus rt x of t minus delta 1 of t s1 of t. And the self-financing condition, the one that, I just covered it up. This condition here says S1 d delta 1 plus ds1 d delta 1 plus S2 is e to the rt d delta 2 plus d e to the rt d delta 2 equals 0. I don't need to prove that. That's taken care of automatically, right? It's taken care of automatically because, again, if you take equation 3, and let me call this equation 4, if you take equation 3 and 4, you go back to 1 and 2. That's where they came from. So these two equations, 3 and 4, will imply 1 and 2, and one, and in particular then implies that the self-financing condition is satisfied. So in the case where we were doing our Black-Scholes argument in stochastic calculus 1, the delta 1 and the delta 2 defined this way would satisfy this self-financing condition. So this is automatically satisfied. I'm not sure if automatically is the right term. I mean, we arranged for it to be. Are you okay with that? Why that's true, that this has to be satisfied? Or good time to ask a question, because if you don't, I'm going to go forward. Okay. Let me now talk about the trading floor argument. The trading floor derivation of the Black-Scholes PDE. If a trader asks you to derive that partial differential equation, or perhaps someone on a job interview, unless it happens to be a graduate of this program, he would expect you to give the following argument. The argument is, let's form a portfolio that is long a call, one call, so it's not going to vary that, and short delta 1 of t, where delta 1 is the delta of the Black-Scholes call pricing formula, shares of stock. Let me call this portfolio N of t. So it's long one call, and it's short delta 1 shares of stock. Let's see, we started out calling this stock S1, so let me persist in doing that. And let's compute its differential. And we'll compute its differential by two different methods. So the first method is you say dn is, and I'll leave the t's out just to save ourselves some time, dn is, I'll have to apply Ito's formula right here to this function c, and I'll get c sub t dt plus c sub x ds1 plus 1/2 c sub xx ds1 minus delta 1 ds1, and I stop there. And then I say, well, c sub x and delta 1 are the same thing, so these two terms cancel. And this term, C sub t, and this term plus 1/2 ds1 is sigma squared s1 squared cxx, right, are both dt terms. And then we say, well, there's another way we can compute this portfolio differential, because at each time I'm holding a short position in the stock that perfectly hedges the risk of the portfolio. I'm delta neutral. And that means that if I move forward in time, the portfolio ought to return the risk-free rate, since it's instantaneously riskless. If it didn't return the risk-free rate, there should be an arbitrage. And so the differential of n should be r in dt. This is the argument you'll see actually in the Black-Scholes paper. And r in dt, well, r in is here, c minus delta 1 s1 dt. And since these are both formulas for dn, we could set them equal. And so we would get c sub t plus 1/2 sigma squared s1 squared c sub xx is rc minus r s1, and delta 1 is c sub x. Right, that's setting them equal. And that's the Black-Scholes partial differential equation. It's arranged a little bit differently from how you usually see it, but if you pull this term to the other side, you see that we have, right, you have to first replace the s1 by real variables, and then put the arguments back in, and you have the Black-Scholes PDE. But you should be a little nervous about this derivation. And at least one issue you ought to be nervous is when I took the differential up here, I did not use Ito's product rule on this product. And in fact, if I had used Ito's product rule, I would have gotten two more terms. I would have also gotten an S1 d delta 1, and I would have gotten a ds1 d delta 1, which I did not write down. So from a mathematical point of view, the formula that's in the usual trading floor argument is wrong. It's missing two terms. It turns out that this formula is wrong as well, and they're wrong in the same way, and the errors cancel each other. Let's try to think a little more carefully about this formula. So n, here's n. N is c minus delta 1s, and the call price and x are always the same. So this is x minus delta 1s, right, coming from here. And x minus delta 1s, here's x minus delta 1s, is delta 2 times e to the RT. All right, are you with me here? Let's see, level. So I'm using these two formulas. X is c, and x minus delta 1s1 is delta 2 e to the RT. So I've used those two formulas there. And then if I take the differential of n, there's a product there. So we'll get, first of all, differentiating with respect to that t, I'll get r e to the RT delta 2 dt. And then I'll get e to the RT d delta 2. And Ito's product rule has a product of differentials. I don't really need to write this one down, but I will, just to be complete, because this is a 0 because the differential here doesn't have a dw tilde in it. And so this term's 0, but I'll write it down. And notice that this term right here is in. And so what we've gotten is r in dt plus two extra terms, e to the RT d delta 2 plus d e to the RT d delta 2. What's the relationship between the term that's in square brackets here with the minus sign and the term that's in square brackets here? Well, the formula at the top of the page says they're equal. Right? This formula says they're equal. And these two terms are these two. If I put them on the other side, then I have them with a minus sign, and that will be equal to these two, which are these two. And so the minus S1 d delta 1 and the plus ds1 d delta 1 is equal to the e to the rt d delta 2 and the differential product, differential of e to the rt times the differential of delta 2. So when we equate our two formulas for dn, these terms cancel out, and we get to the argument, right? We get to the same conclusion that we got before, but now in a more correct way. It turns out that what's going on here, and I think Black and Scholes had the insight to see this. What is going on is that if I move forward in time, this portfolio N is not self-financing, and its value will change for two reasons. So the reason it's not self-financing is because in order for it to be self-financing, you also have to keep track of your cash position. And it's only keeping track of the call and the stock and not how much is in cash. And so this portfolio is not self-financing, and when you move forward a little bit of time, the value of the portfolio changes for two reasons. One reason is that the stock price changes, and when the stock price changes, it changes the call price, and that's what this is keeping track of. And it's also what this is keeping track of, because when the stock price changes and you have a position, then you get a profit or loss associated with that. There's another reason the value of this portfolio changes, and that is because you're continuously rebalancing. And because it's not self-financing, you're having to either put money in or else take money out that goes into this cash position that was never written down. And that second effect is the one that's going on right here. In fact, if you think about it in discrete time, what is that in discrete time? That's the S of tk plus 1 times the delta 1 of tk plus 1 minus delta 1 of tk. That says when I change my position in the stock, S1, I have to pay for that. Right? And this is keeping track of that effect. The other formula, this one, the one that says, well, it's instantaneously riskless, that's true if the only risk you're thinking about, the only change in the portfolio value you're thinking about, is due to the change in the market prices. But there are two effects on the portfolio, change in the market prices and the fact that you're continuously rebalancing and the portfolio is not self-financing. And this term is keeping track of the second one. And fortunately, these two effects cancel each other, right? And so the original argument was right. What they were doing when Black and Scholes wrote this down was they were thinking intuitively, let me just keep track of the change in the portfolio value due to the change in the stock price. And they weren't thinking about the change in the portfolio value due to the rebalancing. And they just equated those two, and that's intuitively correct, and they got the right answer.
Yes. Like, I understood how mathematically things play out, but how did we know that this portfolio is not self-financing? Generally, we always take the assumption that it is self-financing, right?
How do I know that this portfolio is not self-financing? You can actually do the calculations. Actually, it's probably easier to see that this portfolio, that this term is not zero, right? So if this portfolio were self-financing, then let me think of this portfolio. N of t is, I can write it this way, it's delta 3 of C of t S1 of t minus delta 1 of t S1 of t. The delta 3 is always equal to 1. And the delta 1 is the delta of the option. So that's the equation 1, right? I'm looking, here's n rather than x, and I'm saying I have two positions. I have delta 3 and a call, and I have minus delta 1 in a stock. And then equation 2 would say dN is equal to delta 3 dC minus delta 1 ds1. And if the portfolio were self-financing, that's all there is. But in fact, there's more. Now, I don't have to worry about differential of delta 3 because it's a constant. But I do have to worry about these extra two terms. And so that portfolio is financing if and only if these two terms add up to 0. And you can just write them down and see that they're not. And it might be easier to write these two terms down and see that they're not, because these two terms are equal to those two terms. Right? And so this is a little bit easier to check because that's a 0 right there. And this is certainly not. And so you see that that's not a self-financing portfolio. The one that's just long the call and short the stock is not self-financing. Other question? Yes.
So essentially, the portfolio of call and the stock and the money market taken together is a self-financing portfolio, is what you're saying.
Yes. So what I would do is I would take long call, short one stock, not only is it self-financing, but it's also always has price 0. So let me put in here what I would need, and I think the other term is plus so this, of course, this is S1 of t, n of d plus, minus k, e to the minus r, t minus t, n of d minus. And this is n of d plus. And so the other term that I need here is k. I'm going to write it this way. E to the minus r capital T, n of d minus, times e to the little rt. Now that's always equal to 0, right? Because what I've done is I've taken the call price, it looks like this, and I've subtracted off both pieces of it there. And this is the position in the money market account. And this is to the money market account. That one is self-financing. And what would self-financing mean? It means that if you write down the differential, right, you're only going to get 3 terms. Right? You'll get the differential of this, you'll get delta 1 times the differential of this, and you'll get this quantity times the differential of that, and the other terms will, the other 2, 4, 6 terms will all add up to 0. And you don't want to check that they all add up to 0, because if you write it down, you can see that you get a correct equation when you only have 3 terms. Right? So let me not do it, but this one is the one that's self-financing.
This brings a related question. So if you have a portfolio of many derivatives, and suppose I have an initial amount of money, I replicate this portfolio and I dump the remaining amount to the money market account. So will such a portfolio always be self-financing?
Yes. So this is the reason I like equation 3 rather than equations 1 and 2. What you do is you say, well, if you have 2 assets, you only get one choice. So you get to choose how much you want of one asset, and then the other one is funding that. And so the other one then is determined by how much you put in that one. If you have 3 assets, then you have 2 choices. And that tells you how many Brownian motions, and in order to have a complete market, if you have one Brownian motion and you want to do replication, you need one choice so that you can match the dw tilde term. So you need two assets, so you have one choice. If you have two Brownian motions, then you need to choose two deltas, so you'll need three assets in order to have a complete market. Okay, so that's all there is to self-financing, except we made it a little bit more complicated because we did this thing with change of numeraire. And let me then discuss that. I'm glad you're here today, Bob Manu, because you asked me this question, and I blew you off when you asked, and I'm feeling bad, so I'm now going to answer your question. What happens when we do change of numeraire to the self-financing stuff? And so what I'll do is I'll take the equation that we have, let's see. So S1 of t, I'll now just call it S of t. You can think of it as some risky asset. And S2 of t, I'm going to take to be a bond that matures at time capital T, and we'll think about little t's between 0 and capital T. And we'll think about our portfolio, dx. If I take a position delta in the asset S, and then I'm going to write this with only one delta, and so what's in the asset B? Well, I first figure out my cash. That's x minus delta S. That's the amount in cash. I divide it by the bond price. That's the number of bonds I own. And then I go dB there. Right? So this is the equation 3 in this particular case. Right? It's this equation where I'm just calling that S, and the S2 is the bond. Okay, so that's designed to be self-financing, right? That's already self-financing because I've only chosen one delta. I haven't chosen two. And now I'd like to think about what happens if I were to, instead of pricing X, here we're pricing in dollars. And now I want to price in bonds. So instead of X, I want X over the bond price. And then I want to think about what does the differential of that look like. And our intuition tells us it should be the number of shares of S we're holding. But now S is priced not in dollars but in bonds, so the price of S looks like that. And so we should get the change of the price in S, but now denominated in dollars, plus the number of bonds I'm holding, and then the change of the bond priced in bonds. But of course, this is just d of the constant 1, which is 0. And so this term is gone. And that was one of the things that makes our life simpler when we change numeraire. If one of your assets is the bond, then changing numeraire is a good idea because it makes one of the terms go away and all the calculations get easier. And our question is that equation really true? Okay, is that equation really true? And so I'd like to just check that it is. So I need to do some preliminary calculations. So let's remember some Ito rule formulas. First of all, I'm going to need to know what is the differential of 1 over the bond. And Ito's formula says, well, 1 over b, the derivative of that is minus 1 over b squared. So I take the first derivative of 1 over b, and I multiply that by db. The second derivative of 1 over b, if I differentiate again, I get 2 over b cubed. But Ito's formula says you take half the second derivative, so I get 1 over b cubed dB dB. And what is ds over b? Right, that shows up right there. And you could use a quotient rule, but it's a little bit messy. So the reason I'm doing it this way is it's a lot easier to use Ito's product rule. I'll write s over b as s times 1 over b. And then this is 1 over b ds plus s d 1 over b plus ds d 1 over b. And then we come back and fill in 1 over b ds. And now where I have d1 over b, there are really two terms in d1 over b, so I'll write them out. This one multiplied by s gives me, whoops, a minus, not a plus, minus s over b squared db. And this one gives me s over b cubed db db. And now what happens when I multiply ds times db? When I multiply ds, or d1 over b, when I multiply ds times d1 over b, I'll get something out of there. So I'll get a minus 1 over b squared ds db. And I won't get anything out of here because this is already a dt term. And if I multiply a dt term by anything, I get a 0, any other differential. So here's the differential of s over b. Are we happy so far? And now what I want to check is what is dx over b. So again, I'll play this game of writing this as x times 1 over b, and then using the product rule. It's 1 over b dx plus x d1 over b plus dx d1 over b. So the first term I'll just write down, 1 over b dx. No, I won't just write it down because I have a formula for dx. Right? Dx comes from right here. So it's delta ds plus x minus delta s over b db. And then I have plus x d1 over b. d1 over b is right there. Minus 1 over b squared db plus 1 over b cubed db db. And then the product of the differentials. Let's not get carried away here. So when I multiply, well, let me write it down, dx first. So dx is coming from here, delta ds plus x minus delta s over b db. And then there's the differential of d1 over b. I only need this term because, again, this term is a dt. And if I multiply a dt by any other differential, I get 0. So I only need to pick up this term. And so that's minus 1 over b squared db. And now let's just multiply it out. So first term is delta over b ds. Second term is x over b squared db. Third term is minus delta s over b squared db. In this row, I get minus x over b squared db plus x over b cubed db db. This would better work. Last row, there's a minus sign coming from here. I get delta over b squared ds db. I get minus x over b cubed db db. Right? X over b and minus 1 over b squared db. And these are db db. And I get minus delta s over b cubed db db.
The last term be a plus.
Did I mess up somewhere?
The last
Should be a plus, shouldn't it? Good. Okay. So what cancels? Well, here's an x over b squared db that will cancel. And here's an x over b cubed db db that will cancel. and every other term has a delta in it. So let me factor the delta out. And then I have 1 over b ds minus s over b squared db minus 1 over b squared ds db plus s over b cubed dB dB. And what we were hoping to get was delta as the differential of s over b. So here's the differential of s over b. Did we get that? I claim we did, right? 1 over b ds is sitting here. Minus s over b squared dB is sitting here. And these two are reversed. Minus 1 over b squared ds dB is sitting here. And s over b squared dB dB, whoops. That's because I made a mistake when I wrote it down, right? It's a b cubed. This is a b cubed. It's sitting there. So we did, in fact, get delta d s over b. Okay, so the final story on change of numeraire is that if you're denominated in units of bond, and one of the instruments you're trading in is a bond, then when you do that denomination in units of bond, this term just goes away, and you get only one term in the differential of the value of the portfolio. Okay, so I've said everything that I wanted to say about self-financing. Any question that you, of course, you can always ask questions on Friday as well, if you think about it. Any issue you'd like to raise before we press ahead? Okay, let's talk about American options. We're going to take a break pretty soon, so I'm just going to get the discussion started, and then we'll come back and go into more depth in just a moment. The one thing that I need, question?
In the equation, when we wrote x of t is equal to the price of the call minus delta 1, yeah. So how did we get the position in the money market account as k into e power minus rt n of d minus?
So our replicating portfolio, so the question is, how did I get this position? When we did the replication of the call, our replicating portfolio held a stock and cash, or a money market, units of a money market account. And it held it in such a way that the value of the portfolio was always equal to the value of the call. What we're doing now is, rather than having two separate portfolios, one has in it only the call, and the other has stock minus and cash, I'm combining them and say I'm going to take the call minus the other one. So if I do that, then I have the difference would always have to have value 0. So I know that this is going to have value 0 if this is going to work. And I know what this is. It's given by the Black-Scholes formula. And I see what that is. And whatever's left over has to be the other term. That's how I figured it out. And then you can check that it works. Anything else? First, let me remind you of Jensen's inequality. I remember Jensen's inequality is that the expected value of the square of a random variable is always bigger than or equal to the expected value of its mean squared. Right? The difference is the variance. So Jensen's inequality says that if you have phi, a convex function, and you take phi of x, which is like x squared, and then take an expected value, That'll be bigger than if you do it in the other order. And it even works with conditional expected values. So if I take not expected value, but conditional expected values here, it'll be bigger than if I do it in the other order. And what is the other order? You first take the conditional expected value, and then you put that into the function phi. Let's think about American call. I'm going to use a geometric Brownian motion. ds of t is r s of t dt plus sigma s of t dw tilde of t. And we have an expiration date for the call, capital T, and we have strike k. But the American call can be exercised anytime between 0 and capital T. It doesn't have to be exercised at capital T. And the question is, would you ever want to exercise it early? And so the question then really is to compare the call price, and I'll put here E to denote the European call price. That's the one that's given by the Black-Scholes formula. Compare the call price to S of t minus k positive part. We'll call this the intrinsic value. Actually, if you exercise at time t, what you get is S of t minus k. But you would never exercise when S of t was below k. And so the only time you exercise is when S of t is above k, so it doesn't hurt to put this plus sign. It doesn't change anything. And it makes a couple of the equations look a little bit easier. So I'm going to say that the intrinsic value is S of t minus k positive part rather than just S of t minus k. For an American call, it turns out that the call is always worth more alive than dead. That is to say, this value, the European call price, is always greater than or equal to this value. And so you never exercise until you have to at capital T. If you exercised early, you would be sacrificing something that was worth C of t and S of t for something that was worth less. And how do we show that? Well, we just use the risk-neutral pricing formula. So tilde e to the minus r cap t minus little t s of capital T minus k positive part given f of little t. So that's the risk-neutral pricing formula. I'm going to take this discounting term inside. You can always take a positive number inside this positive part. And so I'm write this as e tilde of e to the minus r cap t minus little t s of t minus e to minus r cap t minus little t k positive part given f of t. And then I'm going to use Jensen. And the phi that I'm using here is x positive part, right? It's this convex function. And so here we are with the positive part function on the inside. And Jensen says if you move that to the outside, you'll go down. And so this will be greater than or equal to, so first I take the conditional expected value. And then the positive part. So there's only one random thing in here. So the conditional expected value I can take the following way. Let me write first e to the little r little t, e tilde, e to the minus r capital T, s of capital T, given f of little t. Okay, so what I'm doing with that term is I'm putting part of the r, the r positive little t out, the r negative, the negative r capital T in, and then this term I'm just writing down, and then take the positive part. And of course, the martingale property for the stock price is that this is e to the rt, e to the minus r little t, s of little t, minus e to the minus r cap t minus little t k, positive part. If I throw this away, I'll be subtracting more. I didn't say it, but the interest rate here is non-negative, right? So I'm assuming that r is greater than or equal to 0. So if I throw this away, I'm subtracting more, and so I'll go down. So this will be greater than or equal to s of t minus k, positive part. And in fact, the inequality is strict. There's one place where it's strict for sure, and that's right here when you use Jensen's. Jensen says that if you have a convex function like this, and your random variable has positive probability of being both on this part, on this side, and on this side, then the inequality will be strict. So this inequality will be strict. And if r is strictly positive, this one will be strict as well. And so the European value of the call is greater than the intrinsic value. And so we should not exercise it early.
This proof is kind of constrained to the part when stock follows a GBM, right?
This uses the fact that the stock follows a geometric Brownian. Well, I use the fact that the stock follows a geometric Brownian motion. In fact, if you look at this proof, the only thing that I used here really is the martingale property on that. Right? So if the volatility had been random, for example, and time varying, it wouldn't have mattered. If the interest rate had been random, there's actually, you'd have to think a little bit, but it still works even if the interest rate's random. And so, so this is a very general result. It doesn't need a geometric Brownian motion. What happens if I try this with a put? I'll call that PE of T and S of T. By the risk-neutral pricing formula, that's E tilde of E to the minus R cap T minus little t, K minus S of capital T, positive part given F of T. The first step still works. Take this thing in. E to the minus R cap T minus little t, K, minus e to the minus r cap T minus little t, S of capital T, positive part. How about the next step? Positive part is x, right? Still use right? That thing is still this function. It's still convex. And so I can take the next step in the same way. Right? So Jensen's again will say, so I take the expected value in and do it first. So first the expected value, and then the positive part. So let's see, there's only one thing in here that's random. It sits right there. So I have e to the minus r cap T minus little t, K, e minus e, and I'll play the same game. I'll put the plus r little t out, and the e to the minus r capital T S of capital T in. And then after we get done computing the expected value, we take the positive part. stock price discounted is still a martingale, so this is still e to the little r little t s of little t. And so I come to e to the minus r cap t minus little t k minus s of t, positive part, and now what? I'm stuck, right? Because if I throw this away, things get bigger, not smaller, right? So stuck. And the problem is that e to the minus r cap t minus little t k minus s of t, positive part, is less than or equal to e to the minus e to k minus s of t. Unless r happens to be 0. If r happens to be 0, then it's okay. Okay, so what conclusion do I get here? If r is 0, don't exercise the American put early. And we'll talk harder about the case when r is positive. So, right, think after the break. You can hear a lot of nonsense, and one of the nonsensical things that you can hear is that you don't exercise an American call early because the potential upside is unbounded, right? The call payoff looks like that, right? And the upside's unbounded. But you do exercise an American put early because the upside payoff is bounded. The put payoff, right, looks like that. Well, so first of all, if the interest rate is 0, the upside is still bounded on the put, but you wouldn't exercise it early. Right? So here's a case of something with bounded upside that you don't exercise early. And if you think about what's going on here, the reason for these two is that with the American call, Jensen's inequality says you're better off alive than dead. This inequality right here is the one that says the call price is going to be bigger than or equal to something. And so Jensen says exercise late. My way of thinking about Jensen is that if I have a convex function and I'm putting a random variable into it, the more the random variable is spread out, the higher the expected value that I'm going to get, right? Because if it's convex, I want the random variable to take values out here, not in here. So Jensen argues for exercising late. Let the stock price distribution spread out because you're putting it into a convex function. There's something else that argues for exercising late, and that was this step right here. This step right here. It says that the strike price is something you're going to pay if you own a call. Right? When you exercise, you pay the strike. You'd rather put that off, pay late. Right? And so discounting and late exercise allows you to discount the strike. At the and that's good because of the time value of money. You can put Jensen still says exercise late. But if you're going to get the strike, and you want that sooner rather than later. And so you want to capture strike soon. So capturing strike. Says exercise soon. Unless the interest rate is zero, in which case you don't care. The money has no time value if the interest rate is zero. And this competition between these two things makes the American put problem hard to solve, right? Whereas the American call is interesting. Incidentally, what about an American call on a dividend-paying stock? So if you have a dividend-paying stock, the discounted stock price is not a martingale anymore. You have to put in the dividend rate. That will mess the argument up right at this point. And what happens if you have a stock that's paying a dividend and you have a call on it, if you're sitting waiting to exercise, that stock is paying out the dividend to its stockholders. But if you exercise, you get the stock and you collect the dividend. And because of the time value of money, you may want to exercise early in order to capture the dividend. So then it may be optimal to exercise early. To capture the dividend. None of this has to do with whether there's bounded or unbounded upside. Right. That just totally fallacious argument about the upside being bounded or unbounded. It has everything to do about Jensen's inequality and whether you're paying or receiving. And if you're receiving, you want to do it early. If you're paying, you want to do it late. So let me see. Any question here? So what we're going to do after the break is we're going to come back and we're going to think harder about this competition here for the American put, about wanting to exercise early to get the strike, but wanting to exercise late to allow Jensen's inequality to increase the value. Let me see if there's any question before we take our break. Yes?
So in case of an American put, late exercise is preferred only when R is equal to 0, right?
When R equals, so whether you exercise late or not depends on the stock price. And so you want to, you exercise. If it's an American put and R is positive, then if it gets deep enough into the money, you'll want to exercise it early. It's possible that you would not exercise it early because it never got deep enough into the money before expiration. Right? But if R is positive and it gets deep enough into the money, then you will exercise early. If R is 0, it doesn't matter how deep into the money it gets. You don't exercise until the end. Is that okay? Any other question? Okay, why don't we 20-minute break, because this is the time when you're supposed to fill out your evaluations of the course. And we really do want those evaluations. I want the evaluations because it gives me a chance to get feedback. I got an interesting piece of feedback yesterday, and maybe you want to comment on this on the evaluations. The feedback was the reason the exam was so much harder than the homeworks was because on the homeworks, there's step 1, step 2, first do this, do that, do that, do that. And so you don't have to think, what is it I'm supposed to do here? And on the exam, there's not the step 1, step 2, step 3, step 4. And as I think about that, I realize there's some truth to that. Of course, it won't hurt you, but what I'm thinking about for next year is that on each homework assignment, there would be at least one problem without any steps. And just do this. And you think of the steps yourself, just as a better way to get ready for what's going to happen on the exam. So that's a suggestion I got yesterday. I find it pretty intriguing. And if you want to make a comment about that, you're certainly welcome to do so, or anything. Another thing that I'm thinking about is what is the homework policy? One homework policy that I'm considering is just making them totally optional. And if you turn it in, we'll grade it and give it back to you, and you'll get the feedback. But if you don't turn it in, no harm done, and the scores, the grades in the course will be based on the exam. If you think that's a terrible idea, you might want to tell me that in the evaluation. If you like that idea, you can tell me that as well. So other things that you're thinking about, I'd be interested to hear. So let's take 20 minutes. I have homeworks. Yeah, so while you're thinking about homeworks, I have homeworks, and I will spend some time returning them here. Hello. I wasn't checking it. Luke Hal? Yu Zhang? Wan Su Li? And Yushua? Zhang is the last name. R-U-O-S-H-U-I. Bingwei Sun. Yin Liang. Zeihua A.I. How do you pronounce A.I.? I. Okay, so it's not so hard. I shouldn't be able to do that. Srinivas Kumar Sankara. Alex Maleska. Lin Ping Jing. Andrea Mazanto. Shi Liu. Sushant Chowdhury. Kartik P with a long last name. Catherine Monk. Lee. Z-H-U-O-Y-U. Chen Wan. Marlon Downer. Chetan Shinoy. Nathan Faber. Andrew Linsky. Yuan Chen. Wyman Ma. Ching Zhong. Yali Xu. And more of a Pele, I think. Felipe Restrepo. Young, Stephen Liu, Jia Xu, and Sai Managala. You're welcome. And I have one homework that doesn't have a name. It has 20 points on it. You may want to claim it. So if this looks like yours, let me know. That was a homework 4, actually. Let's do homework 4. Yali Shu, Marlon Downer, Shi Liu, Jing Zhang, Dai Shu, Shunji Liu, Zhou Yu Li, Catherine Monk, Andrew Litsky, Alex Valesco, Jing Hu, Pucci Lu, Sai, Alroy Ko, Jehua Ai, so I think this is there, right? Ying Liang, John Rushua, Ruoshui, Ching Shen, Kartik Parama, Yunling Yi, Malcolm Fillier, Andrea Musante, Felipe Castrepo, Srinivas Kumar, Nathan, Mary Borges, Nanda Moravella, Pollock, Yifan Wang, Xing Yang, Stephen Liu, Lily Gao,
volatility circle thing, but here the interest rate is constant. So we get the same result.
You have this same kind of equation, but with r equals 0.
Sorry?
So you'll use this formula with setting r equals 0. So in the homework, where you're trying to compute the volatility surface.
Right.
You,
I mean, I'm not talking about homework. I'm saying here to deduct this relationship. First of all, we assumed for the stock processes R is determinate or constant.
yeah, that's right.
If we have it like not constant, can we still get the same result?
No, we don't get this result if R is
Okay.
so if it's no, I'm sorry. If it's deterministic but not constant, you could still get this result. But if it's random,
Okay.
then you don't get this result.
Okay. So in homework, it's not only deterministic, but it's also constant as 0.
Yes, it's constant and equal to 0 in the homework.
Yeah. Okay. Thank you.
Looking for some homeworks? Mm-hmm. No, except I got them scrambled, so. The first one's anonymous. No. It will be on the bottom. Actually, it will be on the bottom probably because I called your name first and reversed the order.
Okay.
Oh, that's mine. Okay.
So I have a homework.
3, and I
Have home.
also,
You didn't get homework 4, right?
no.
So we didn't see yours?
It's okay.
It is on the bottom. Yeah, so I'll get, yes. I'll get those in a minute.
I was worrying about this homework because I don't know grade. Other people got grade.
Yeah, Ted started putting up the grades before he had finished grading.
Yeah, I met him yesterday and he told me there was one without name and I thought maybe.
Oh, yeah, and that is true. We have one without a name. Yours was on printed out, right? You submitted yours on
by
Blackboard.
paper. No, by paper.
Oh, okay.
Yeah, this one. Good.
You know, it's time to start again. So why don't I take it during the next break?
Question. So, can I think in the intuitive way that for the self-financing, the change of the price is just caused by the change of the stock price, not by the
Change in the
by the
position.
position, right?
That's right. That's exactly what it is.
And for these two kind of calculation, they get the same result. So, is it a detailed way to do this? I mean, they get the same result. This is a more intuitive way,
Yeah.
and
This is actually checking that the stochastic calculus confirms the intuition.
so for this. I also think we maybe I can use the parity to prove this. Is there any possible to use the
Put call parity. Put call parity doesn't hold for American options. It's only for European.
I mean for the European option because at first we just want to prove the European call option will not be exercised before the expiration date. So maybe
I'd have to think about the put call parity. So that might,
I just figure out maybe after.
yeah, that might work. I haven't thought about that. Yeah, let me.
It works.
Okay, that's a good idea. Well, let's see. I was already turned on. Sorry for you guys in New York. I didn't realize I was turned on. On the other hand, I didn't give out any passwords or other secrets. So I'd like to return to this problem of the American option, the American put. And to think about the American put, it's actually easier to think about first a perpetual American put, which is not traded. So this is a creation of mathematicians, but it helps us understand what's going on. So a perpetual American put is that I give you a strike price, So here's time. Here's some initial stock price. Here's a strike price. And I tell you that you can exercise whenever you want to. This thing never expires. And when you exercise, you will get the put payoff at the time you exercise. So you receive this at time of exercise. So what do you think? So I don't know immediately what's the optimal exercise strategy, but what kind of strategy would you look for? I mean, what do you what would you think about this problem? When should you choose to exercise? Certainly you want to wait until it gets into the money, right? Would you do the following? So you got into the money here, right, I'm below K. And so I'm into the money, and I think, well, it might go down, it might go back up. I hope it goes down. Let's wait a while longer and see. And it goes back up. And it comes back to the same level again. Now, the last time you were at this level, you didn't exercise. Do you think you might exercise this time? Well, if you're an optimizer, whatever thought process you went through last time that convinced you that you shouldn't exercise, it still applies because this thing is perpetual. It never expires. So this time is just like last time. You have infinitely long to wait and make your decision. So if you decided last time not to exercise, you should decide this time not to exercise at that level. And in fact, what you should do is there's going to be some level, L, and you say, if it ever gets that deep into the money, then I'll exercise. Right? So there should be some level, and you're going to exercise the first time it gets to there. In particular, time doesn't matter. And so if I think about the price of the put, stock price on this axis, I'll call that X. And I'm putting put price on this axis. And here's the intrinsic value. So this is K, and this is K, and this is K minus X. And there's some level L. And if the stock price gets down to L, you'll exercise and you'll take the intrinsic value. And presumably then for all lower values of the stock price, anywhere below L, you would exercise and take the intrinsic value. But if the stock price is above L, you think the put's worth more alive than exercised. And so you think the put price looks something like this. You know, bigger than the intrinsic value. And obviously bigger than zero, right? No matter how big X is, no matter about how big the stock is, this put always has some value because you just sit and you're going to wait and eventually it'll get down to L and then you'll exercise and you'll make some money. Now, it turns out that this is the right form. This is what the value of the put looks like. So part of the time it's the intrinsic value and part of the time it's not. And in the time when it's not the intrinsic value, the put price will satisfy the Black-Scholes equation. So over here, we'll have the Black-Scholes equation. Let me call this function P of X for put. It's a function of the stock price X. And what does the Black-Scholes equation look like? It looks like Rp of X minus Rxp prime of X minus 1/2 sigma squared P double prime of X is 0. Normally when we see the Black-Scholes equation, we see a time derivative, a theta. But in this case, the time to expiration is always infinite, so you don't care what time it is. And so the price of the put doesn't depend on t. It's just a function of x, and so there's no time derivative showing up in the Black-Scholes equation. So let's think about solutions to this equation. And this is why I'm talking about the perpetual American put, because the time variable is gone. And then we can solve this equation. In fact, the solutions to this equation look like x to a power. If you try p of x equals x to a power, then p prime of x is alpha x to the alpha minus 1, and p double prime of x is alpha times alpha minus 1 x to the alpha minus 2. And if you plug into this equation, the x is to the power alpha in every term. P of x has an x to the power alpha. P prime has an x to the power alpha minus 1, but it's multiplied by x. So you have here an x to the alpha. And P double prime has an x to the alpha minus 2, and you guys let me get away with that, didn't you? The Black-Scholes equation has an x squared right there. And the x squared then brings the power back up to alpha. So if I plug this in, there's going to be an x to the alpha in every term. I'll factor it out. And then here, I'll just have r. And then here I'll have minus r alpha, right, because the p prime has an alpha in it. And here I'll have minus 1/2 sigma squared alpha, alpha minus 1. And that's a quadratic equation in alpha, and so we can solve that. In fact, let me pull this out and look at it. This is not 0, so this has to be a 0. And so I have a minus 1/2 sigma squared alpha, alpha minus 1, minus r alpha plus r equals 0. I like quadratic equations that start with plus signs, so I'm going to multiply this by minus 1. 1/2 plus 1/2 sigma squared alpha, alpha minus 1 plus r alpha minus r equals 0. I like quadratic equations that start with a 1, so I'm going to multiply through by 2 over sigma squared, so the first term becomes a 1, plus 2r over sigma squared alpha minus, what am I multiplying by? 2 over sigma squared. 2r over sigma squared equals 0. So what I have here is alpha squared plus, and then this minus 1 becomes a 2r minus sigma squared over sigma squared alpha minus 2r over sigma squared equals 0. This factors. In fact, you get an alpha minus 1 and an alpha minus plus 2r over sigma squared, I believe. Let's see, will that work? If I multiply this out, I get alpha squared, and then I get a minus 2r over sigma squared alpha, and I get a minus alpha, and I get a minus 2r over sigma squared. So that didn't quite work, but I didn't do it right. Minus, this is a plus. Now it works better. And so that factors.
How do we conclude that it should satisfy the Black-Scholes PD? Is it because it's equivalent to a put since we are not exercising?
I'm thinking that it satisfies the Black-Scholes equation because if I'm in a region in which I'm not exercising, it's a lot like an American, a European put. Actually, what I'm going to do after we get through this derivation is I'm going to come back and give you a rigorous argument for why we've gotten the right answer. So this is a little bit heuristic at this point, and we'll come back and make it rigorous. Well, now I have two solutions, right? So there's alpha equals 1, and there's alpha equals minus 2r over sigma squared. And in fact, what happens is that because we know that x to the alpha works as a solution for either of these values of alpha, we can actually combine them. And we can look at p of x equals some constant c1, x to the minus 2r over sigma squared, plus c2 times x to the power 1. But this term can't be in our answer because when x goes to infinity, this goes either to plus infinity or minus infinity, depending on the value of c, and our function is going to go to 0. So this term has to be gone, right? The c has to be a 0. And then c positive will make this term look like that picture, right? As we go to infinity, it runs down to 0. So our solution, we take this solution with C1 positive. Now, what do those functions look like? Right, so I'm looking at functions of the form C1x to the minus 2r over sigma squared. Those all look like this. I'm saying those because I can take different values of C1, right? So there's one of those functions. And then if you increase the value of C1, you'll get a function that's higher. And if you increase the value of C1 some more, you'll get a function that's higher. Now the function we want it to touch this 45-degree line, right? Because we're going to come off of this 45-degree line. So let me put my 45-degree line in here. So I'm not going to be able to use this function because this function never touches the 45-degree line. I could use the other two. Which one do you think we should use? If you're the owner of the option and you say, I'm going to exercise the first time the stock price gets to here, then the value of your option before you exercise it is on this graph. Or if you say, I'm going to exercise the first time the stock price gets to here, way deep in the money, then the value of the option before you exercise it is on this graph. Which graph do you want to choose? I hope it's obvious, right? You'd like to choose this option. And let me call that value of L. I'll give that a special name. I'll call that L star. And we'd like to figure out what that number is. So what's special about L star? Well, the first property is that if we look at C1 L star to the minus 2r over sigma squared, then we're on the graph. This is the graph k minus x. So that would be equal to k minus L star. But we have two unknowns. We don't know what the constant C1 is, and we don't know what the value of L star is. What is our second equation? Second equation, because you'll need it in the numerical analysis course to solve numerically for the finite horizon puts, the finite expiration date puts. What's the second equation?
The derivative at the derivative of the price at L star should be 1.
The derivative of the price at L star should match the derivative of this line, right? Which is actually minus 1, right? So I need the tangency condition, right? So I need the derivative. So what is the derivative? It would be minus 2r over sigma squared C1 L star to the minus 2r over sigma squared minus 1, right? That's the derivative of this. Evaluated at L star, that should be minus 1. Okay, so I have those two equations.
Can you please explain as to why the derivative should be 1? Because the curves can intercept, even when then they have different slopes, right?
Minus 1, pardon me. So this is a tangency point, because if it were not a tangency point, this graph would pass below. Right, so what you would do is if you So there are two ways it could fail to be a tangency point. It could fail to be a tangency point because the graph went that way, or it could fail to be a tangency point because the graph went this way. Now, obviously, you don't want to put your L at this point because then here's the value of your call. Right? If I'm going to say I exercise here, and here I don't exercise, and then I'm using this to give me the price when I don't exercise, it's below the intrinsic value. So I don't want to see that picture. And I don't want to see this picture either, because this picture would, let me continue it on, would look like that. And I'd say, oh, I should do this picture instead. Well, not that one. I should pick a higher function. And so I don't want my function to cut through the 45-degree line. I want it just to be tangent at the 45-degree line. And that's this condition. The left-hand side here is the derivative of the function at L star. On the right-hand side, once I corrected it, is a minus 1. Well, we can all do the algebra, or you can watch me do the algebra. Let me just tell us the answer, and we'll check it. What you want to do is you want to take L star to be 2rk over 2r plus sigma squared. And you want to take C to be k minus L star to the 2r over sigma squared. And let's just check that that works. So there are two equations here, equation 1 and equation 2. Equation 1, if you plug this in for C, then C1, k minus L star, and then L star to the 2r over sigma squared. So that's the C1, and then I have the L star to the minus 2r over sigma squared equals k minus L star. So that works. And the other equation, 2, says minus 2r over sigma squared. C1 is k minus L star over L star to the 2r over sigma squared. And then we have L star to the minus 2r over sigma squared minus 1. And we're asking, is this equal to minus 1? Well, the left-hand side has a partial cancellation. The left-hand side is minus 2r over sigma squared, k minus L star over L star. And we're asking, is that equal to minus 1? So let's think about what is k minus L star. That would be k minus 2rk over 2r plus, I don't know what sigma star is. Let's say that was a sigma squared. So that's 2r plus sigma squared k minus 2rk over 2r plus sigma squared. So that's sigma squared k over 2r plus sigma squared. So k minus L star over L star multiplied by 2 minus 2r over sigma squared is minus 2r over sigma squared. Then we just worked out the k minus L star. That's sigma squared k 2r plus sigma squared. And then we have L star in the denominator, so I turn this upside down. 2r plus sigma squared over 2rk. And I hope that's a minus 1. I think so. Yeah, everything cancels and I'm left with a minus 1. Okay. And, you know, solving the two equations and two unknowns is not hard. I just prefer to go ahead and give you the solution and then we check it. And so now I have a formula. I have a formula for what I think my call price looks like, and this was actually page 13. Let's go back to where we were talking about it. I think my call price looks the following. So in this region, it's the intrinsic value, k minus x. That's for small values of x when the stock price is between 0 and L star. And then for large values of x, it's given by this formula. It's given by this formula. And the C1 is k minus L star. It's given by this formula. It's k minus L star over x to the 2r over sigma squared. Right? That's this formula with C1 equal to this constant. And it has 4 properties. First of all, it's everywhere bigger than the intrinsic value. Picture that we used to construct it. And what we did was we said we have these hyperbolas. I picked the one that's tangent to the intrinsic value, and on this piece below L star I take the intrinsic value as my function p, and on this piece above the intrinsic value I take the hyperbola as my function p. So sometimes my function p is equal to the intrinsic value, sometimes it's strictly greater, but it's everywhere greater than or equal to. Secondly, if we look at the Black-Scholes equation, Rp of x minus Rx p prime of x minus 1/2 sigma squared x squared p double prime of x, some of the time that's 0, because that's how we found our function. Right? We said we're looking for a function that satisfies the Black-Scholes ordinary differential equation in this case, and as long as we're looking on this parabola, so bigger than or equal to L star, then we get a 0 out of this. If we look to the left of L star, we actually get a positive number, so I'm going to say this is everywhere greater than or equal to 0. And why do I say it's greater than or equal to 0? Well, let's look to the left of L star. So if p of x is equal to k minus x, then this thing, r p of x, is r times k minus x, minus rx p prime is minus 1, and then p double prime is 0, right? If p of x is k minus x, the second derivative is 0. So we only get this much. And here we have a minus rx, and here we have a plus rx, so they cancel. So I get an rk, and that's greater than 0. So either I have the Black-Scholes equation, or I have this quantity is equal to rk, which is bigger than 0. Thirdly, for each x except x equals L star, we have equality in either or two. Some of the time, when x is small, we have equality in 1. P of x is k minus x, positive part, which is k minus x. And sometimes when x is bigger than L star, then we have the Black-Scholes ordinary differential equation. And at L star, we have a little bit of a problem because although the first derivative does not jump when we go across L star, we made sure the first derivative didn't jump because we took the hyperbola that had slope minus 1 here, which is the same as the line. The second derivative does jump as we go across L star, and so there's no well-defined second derivative at L star. So I'll not think about this term when x is L star. And the fourth condition we have is that P prime at L star is minus 1. Okay, so I've gotten a function that has all those properties. I'd like to now do the rigorous thing. I'd like to check that this function has a right to be called the price of the American option, the American put. Yeah.
When it comes to point 3, even when x equals L star, you have the first equality, right? Like that k minus x plus would still be satisfied at x equals L star.
Oh, yeah, that's true. When I have x equals L star, this one does hold with equality. That's right. So I guess I could say one of them holds with equality. Right? This one is undefined, but the other one does hold with equality. That's a good point. So just mark that out. Another question. Yeah. Sai?
What's the reason for plugging in this value of px in the Black-Scholes equation and seeing what the behavior is?
Why did I use the Black-Scholes equation?
Yeah, I mean, why are we plugging it into the Black-Scholes equation, seeing if it's greater than 0 or not?
Because I'm about to show you that this thing now has the right to be called the price of the put, the American put, and I need this inequality to show you that.
It's a perpetual put, so it will be completely different from the Black-Scholes PD that we have derived, right? I mean, I would expect it to be.
Oh, it's a completely different function from the solution to the Black-Scholes PDE.
The PD itself, I mean, how can we be sure that the PD itself might be different, right?
So for the American option, the PD, so what happens with the American option, in general with American derivative securities, is that there are two regions in the space, in time space. One is the region in which if your stock gets into that region, you want to exercise the option. And the other is the region in which if the stock is in that region, you want to let the option continue, do not exercise. So in the region where you exercise, you know what the price of the option is. It's the intrinsic value. In the region in which you don't exercise, the price of the option will satisfy the Black-Scholes PDE. And we haven't, I mean, I've just told you that and I've used it. I haven't verified that that's the right thing to do. So that's the next step, is to check that, okay, now that I've got this thing, let me check that it really is the price of the option. Yes?
Professor, I have a doubt regarding the notion that our exercise barrier L will be constant over time. So if we wait longer, we would want our option to yield more because of time value of money. So shouldn't L decrease as we wait for longer?
Well, I'm reminded of you know, there's this thing about if you're investing in, if you're in a trading competition and you took a position and it's lost money, and then you're thinking, should I sell this or not and take the loss? And the question you should ask yourself, well, if I didn't own it, would I buy this? Because if the answer to that question is no, then you should sell it. And it's kind of like that, right? That what that question forces you to think about is it forces you to forget about history. Right? If I didn't own this, would I buy it? That is, forget about the history. Forget about the fact that I've lost money. At this price, would I buy it? And as long as this option is perpetual, right, every time is like every other time, because what really matters is not what time it is, but how long is it until expiration. And the answer is always the same. And so if at this price I would exercise it today, then at this price I should have exercised it yesterday. At this price I would exercise it tomorrow. That's my intuition. You don't have to be convinced by that, because what I'm going to do next is show you that this function that we've produced here has a very good reason to be called the price of the option. And so let me show you that, and then we can have our discussion about whether you believe that this is the price of the option or not. So why is this the price of the option? So let's start with with initial stock price. And then our stock is given as a geometric Brownian motion in this example. And I'm going to put the stock into this price and discount. And then I'm going to take the differential. So looking at the discounted option price, the usual kind of calculation we do, and we'll get the usual kind of thing. We'll get e to the minus RT multiplying every term, and then we'll get a minus RP dt. We'll get a P prime ds, and we'll get a 1/2 P double prime ds ds. You have a right, by the way, to ask at this point, can I use Ito's formula if there is no second derivative at some point? Right? P double prime doesn't have a second derivative at L star. It has a first derivative everywhere because we fixed up the first derivative by this tangency condition, but it doesn't have or the second derivative jumps as I go across L star. And in fact, you can use Ito's formula if the second derivative jumps at points. You cannot use Ito's formula if the first derivative jumps. So the second derivative is okay, but if the first derivative jumps, so if you see a kink, like a positive part function, you cannot use Ito's formula. So we're going to go ahead and use Ito's formula here. And what I'll get is, first of all, I get dt terms. And those are minus rp plus rsp prime plus 1/2 sigma squared s squared p double prime dt. And then the ds has a dw tilde in it as well, e to the minus rt sigma s p prime dw tilde. Sometimes this is 0. This is the dt term. And sometimes it's 0 when the Black-Scholes equation works, and sometimes it's not. And in the times when it's not, it's actually minus rk. This is the negative of what we had here. Right here we had plus rp and minus rxp prime. Here we're going to get minus rp and plus rsp prime. So here we're looking at the negative. When we computed this, and x was below the exercise level, we saw that this expression turned out to be rk. Now it's going to turn out to be minus rk because it's the other way around. And so what we get here is e to the minus rt, rk times the indicator that the stock price is below L star. When the stock price is above L star, we get a 0 out of that term, dt. That's a minus rk. And plus e to the minus rt sigma s p prime dw tilde. Let me form a replicating portfolio and try to match this. So the replicating portfolio is the usual thing. dx is equal to delta ds plus r x minus delta s dt. If we discount that, then the discounting kills the rx dt term, and the other terms get multiplied by a discount, e to the minus rt delta ds minus rs dt. And ds minus rs dt is, from here, is a sigma s dw tilde. Well, I can match that, but there's this term as well. So what I'm going to do is, in my replicating portfolio, I'm going to allow myself to take money off the table. So in addition to hedging this derivative security, sometimes I want to take money out of my portfolio. So I'm going to allow myself to do minus c of t dt. Minus c of t dt. Minus c of t dt. And then we can do the matching. The number of shares of the stock that we want to hold each time t to match these dw tilde terms would have to be the usual thing. It's the delta of the option. And the C of t matches this will be minus RK indicator S of t less than L star so I'm going to sell the option. Wow, how did we get to page 5?
Are we assuming that C of t is from the discounted cash flow? Or
Yeah, so actually I forgot. So here it's C of t, and here it should be e to the minus RT C of t. Yeah. Thank you. At times z, sell the option. So sell the American put. For price P of S of 0. Then use delta of t, C of t on the previous page. If you do that, then you've matched these two differentials. And so at each time, the value of my replicating portfolio is equal to P of S of t. And remember, P of S of t is always bigger than or equal to S of t minus k. And that's property 1. And so what I'm going to do is I'm going to sell you the option for this price. I'm going to put on this hedge. I'm going to consume sometimes. But at every time, the value of my replicating portfolio is P of S of t, and that's bigger than or equal to the intrinsic value. So I'm just sitting there waiting, and eventually you will exercise. And when you do, I have enough money to pay you off. Now, what's this business of consumptions? What's going on there? Well, the consumption only kicks in if the stock price gets below L star and you're asleep and you don't exercise, because you should exercise there. But if you don't, what's P prime there? So if S of t is below L star, the delta, right, it's P prime of S of t. What is P prime below S, below there? What is P prime in here? Minus 1, right? This is minus 1. So my hedge is short 1 share of stock. How much cash do I have? Well, the total value of my portfolio is P of S of t. And in that region, P of S of t is K minus S of t. There's the short stock position. So I must have K dollars in cash. So I'm sitting short. I am sitting with K in cash, short 1 share. What happens if you exercise? You take my cash and give me a share of stock, right? That's what the put is. You sell the stock for K dollars, right? So you give me the stock and I give you the cash and I come out even. What happens if you don't exercise? I earn interest on my cash, right? I just continue to sit there short 1 share waiting for you to wake up. But while you're sleeping, I'm earning interest on the cash position, and I'm consuming it. And that's what the CK is about. I'm earning interest on my cash, and I'm just taking it off the table because I don't need it to maintain the hedge. So I would argue that at least if we use the price given by this function P, the guy who sells the call is protected. Right? It's enough money for him to put on a hedge and maintain the hedge all the way until exercise occurs and then pay off the call, pay off the put. Let me see if you agree with that statement. So there's two parts to the statement. And one part is that the seller of the put is happy with this price. Right? I'd be glad to sell you a put for this price because I can hedge the position. And maybe you'll mess up and I'll get to make some money. I'll get to consume some if you don't exercise at the right time. So
just a question regarding C of t. Like when you differentiate, you'll have a C prime t term as well, right? No, the previous page. Like if you have dx equals C of t dt, I mean,
I'm sorry, D
you have the C of t.
here.
Yeah, so when you discount and differentiate, shouldn't we have two terms?
No, when this is the only term that will show up. So if let me do it here carefully. So I start with dx is this line, delta ds plus r x minus delta s dt minus c dt. Let me break it out. Delta ds plus rx dt minus r delta s dt minus c dt. And delta, here's a ds and here's a minus rs dt, and ds minus rs dt is sigma s dw tilde. So let me go ahead and put that in. Sigma s dw tilde plus rx dt minus c dt. And then if I discount, so differentiating with respect to the t up there, I get a minus r e to the minus rt x dt, and then I get an e to the minus rt dx of t. And in the dx of t, there is an rx dt, and when I put the rx dt in here, it'll cancel that one. And then I'm left with these two terms, and they're both discounted. And so I'll get e to the minus rt delta sigma s dw tilde and minus e to the minus rt c dt. And I hope that's what I have here. E to the minus rt delta sigma s dw tilde minus, and once you pointed this out, the e to the minus rt goes in here, c of t dt. Okay, so my argument is that at least if we use this function p of x as the price of the put, the seller is happy with this price. He can hedge his short position when he sells the put at this price. Would he be happier with a lower price? Could the seller accept a lower price? And the answer is not if the buyer exercises optimally. And by optimally, I mean the first time S falls to L star. Obviously, the price can't be any lower than the intrinsic value. So this part of the price is certainly not too low. not too high. Is this part too high? Well, what's happening here is that that's the price that we computed out here in this region. Could the buyer accept any lower price out here? And what I'm saying is that if you sell this thing and the purchaser of the put exercises the first time it gets to L star, the buyer never gets to consume, because the buyer's consumption only kicks in after the price falls below L star. And so up until that time, there is no consumption going on. These C terms, this C term and this consumption term, they're both 0. And we match the DW tilde terms in the usual way. We do the usual hedge, and if the seller had started with any less money, this thing wouldn't work. So he needs this much if the purchaser of the put is going to exercise it in the optimal fashion. And so this is my argument that this is the right price. And it hinges on the fact that we have the Black-Scholes equation in the region in which the put price is not the intrinsic value, because in that region there is no consumption going on for the seller of the put. So as long as S of t is bigger than or equal to L star, seller does not get to consume. Needs the full initial price of the put to construct his hedge. And the only thing that's left is to say, okay, so suppose the put has a finite expiration date. So here's a time, capital T. This is our time axis. Here's the expiration date. Here's the stock price. Here's K, the strike price. The put is in the money down here. So down here the put price is K minus X. Up here the put price is 0. Down here, the put price is K, e to the minus R, cap T minus little t. That's if the stock price is 0. If the stock price is 0, then what should you do? No. The stock price is 0, you should strike this. Just K, right? The stock price is 0, just exercise. And there is a boundary between these two. And down here, the put price, this is where we have K minus X. You exercise in this region, and you get K minus X. And if you look at the Black-Scholes, and now it's a PDE, RP minus P sub T minus RX P sub X minus 1/2 sigma squared X squared P sub XX. It's equal to RK. And up here, the put price is strictly bigger than the intrinsic value. And RP minus P sub T minus RX P sub X minus 1/2 sigma squared X squared P sub XX. It's equal to 0. And on this boundary in between, the derivative P sub X is equal to minus 1. for the same reason that we saw before. If you compute the derivative below, it's a minus 1. And so you want the derivative above to also be a minus 1 so that these things fit smoothly together. So what you've got is some function here that's a solution to the Black-Scholes equation. And up here you've just got a 45-degree slanted surface. And you want the function to smoothly join the surface. And you have the same 4 conditions. I won't write them down. Well, I'll just say them. They were here. The put price is always bigger than the intrinsic value. If you plug into the Black-Scholes, and now it's a partial differential equation because the theta term is back, it's greater than or equal to 0. For every x, you have equality in either one or the other of those equations. And at this boundary that goes between them, the x partial derivative of the put price is minus 1. And there's, so in the early days of quant finance, every couple of months, somebody would send me his solution for how he had gotten an explicit formula for the price of the American put. And of course, it was like solutions to Fermat's last theorem. They were all wrong, of course. But finally, mercifully, that's died down. Nobody knows how to compute an explicit price to the American put problem. At this point, you have to do it numerically. And this is one of the things that you'll do in the numerical methods course in the fall, is take these conditions that I've written down and figure out how to compute the function that satisfies all these conditions. So I've come to another good break time. Let me see if there are parting questions before we come back. And in the last little bit of time we have, I'd like to talk about the reflection principle. Any question before we go? Yes, I.
So we constructed the replicating portfolio by taking differentials of the discounted asset prices, right? In the case of a perpetual put.
Yeah.
But if it's perpetual, what does the notion of discounting mean there?
I don't know what the discounting means, but I know that's the thing that I have to do. Right? I'm not sure I have a... Right? We have this mean rate of return R here on our stock price. So there is some notion of rate of growth. And I have to discount that out because I want to compare martingales to martingales. And so I need to discount that out. So I'm not sure that I have an interpretation when the... Well, even if the put is perpetual, there is still a notion of time value of money.
You are taking e power minus RT, right? So the T in case of infinity...
Yeah, so I am here fixing a time that I'm calling 0. So I fix, April 30th and call that time 0. But as my put progresses, what matters with an option is not what the calendar time is, but how long it is till expiration. And so even though I have a notion of calendar time, the time till expiration is not changing. Right? So I'm discounting in calendar time, but the put doesn't depend on time because the very first homework problem ever was this reversal of time. And you want to think about things in terms of time till expiration, and the time till expiration is always infinity. And so the time is gone out of the problem, is gone out of the formula for the price. But this is a good point, that I still am discounting because there's a mean rate of return on the asset price S, and I discount it out because I want to see martingales and compare martingales to martingales. Anything else? All right, so why don't we take another 10 minutes so we're fresh when we start talking about the reflection principle. All right, I just cannot wait to tell you about the reflection principle. It's so exciting that even at the end of a long evening, you want to know about this. And we'll begin with the picture that's on the front of your textbook. And so that looks like this. We have a Brownian motion, and we're interested in three levels. One of them is W, one of them is M. The distance between these two is M minus W, and then we go the same distance above M, and that would take us up to 2M minus W. So this distance is also M minus W. And I'm interested in the following. I'm going to go out to time t, and I'm interested in paths that start at 0. This is the path of a Brownian motion. It gets above M, but then it falls back, and by time t, it's below W. Okay, so it gets above M, and then it falls back below W. Each time you see a path like that, you can create a reflected path, and what you do is you go here to the first time it reaches M, and then you just do a mirror reflection around the line up at level M, and I may not be able to do this very well. Like something like that, reflected path. If the original path is below W, then the reflected path will be above 2M minus W. Right, so this says, if you think about these paths, of course they both have 0 probability, but let's think of them as having the same probability. So the path we're looking at is, let me define M of t to be the maximum of the Brownian motion up to time t. So I'm looking at, did the maximum of the Brownian motion get above M, but at the final time the Brownian motion was below W? And that's the same as the probability that at the final time the Brownian motion is above 2M minus W. Okay, on the left-hand side I'm counting the paths that go up and come back, and on the right-hand side I'm counting their reflections, which end above 2M minus W. Now, I know what this probability is because this is a normal random variable with mean 0 and variance t, and so this would be 1 over square root 2 pi t integral 2m minus w to infinity of e to the minus w squared over 2t dw. And let me make the change of variable in there, that x is w over square root of t, so dx is dw over square root of t. And so where I have dw, I'm going to put dx, and then I don't have this t in the square root anymore. I just have 2 pi. E to the minus x squared over 2. So when x starts at 2m minus w, the lower limit of integration, I'm sorry, when w, this was a bad choice. Let me call this y squared. dy. Sorry about that. I have w doing too many things. It was both in the limit of integration and variable of integration. So let's call that y squared and make the change of variables x at y over root t. When y is at 2m minus w, x is at 2m minus w over the square root of t. And then it goes up to infinity. I would like to get the joint density of these two random variables, the Brownian motion at time t and its maximum at time t. And what I'm thinking about here is some kind of pricing some sort of exotic option, right? If I have a knockout barrier option, I not only want to know where does it end at the final time, but did it get above the barrier at some time in between? And so I need a joint distribution of the maximum and the final position. And once you have that, then you can get it. What you would do is just differentiate this with respect to m and w. So you take the square root, the differential dm dw of this probability. Now, if both of these were less than or equal to signs, and I took this mixed partial derivative, I'd get the density. But since one of them is a greater than or equal to sign, I actually won't get the density. I'll get the negative of the density. So let me put a minus sign here. And this will be the density of m of t and w of t as functions of m and w. So the m and the w sit right there. You take the derivatives. We can all do that. Let me just write down the answer. It's 2m minus w over t square root 2 pi t e to the minus 2m minus w squared over 2t. The m here, because it's the maximum, has to be greater than or equal to 0. The Brownian motion starts at 0, so its max is always greater than or equal to 0. The w has to be less than or equal to m, less than or equal to its maximum. And if you plot the region in which this density exists, it looks like this. If the m is greater than or equal to 0, and the w is less than or equal to m. From that density, you can compute lots of things. So, for example, you can compute the marginal for m. So you would just take that density and integrate it from m to infinity. I'm going to compute the marginal for m, so I have to integrate out the w. So that's not right, what I just said. I want to go from minus infinity to m. Right? I'm integrating out the w here, so I integrate up one of these lines, the density that we have. And if you do that, you're going to get 2 over square root 2 pi t e to the minus 2m minus w squared over 2t. If you differentiate this with respect to the w variable, what happens? This 2 and the exponent will cancel this 2. The t here will go down here and give you this t that you see. It's a net positive on the w, a minus here and a minus here, so the sign is right. And then when you differentiate this 2m minus w squared, you'll get a 2m minus w, which is what that term's doing there. And this is evaluated at w equals minus infinity and at w equals m. When w is equal to m, you get 2 over root 2 pi t e to the minus m squared over 2t. And when w is minus infinity, you get 0. And that's twice a normal density. The m here is greater than or equal to 0, so what you've got is that you've taken a normal density and you've folded it over. Right? You've put twice the normal density on half the line between 0 and infinity. In fact, you can see exactly why that's going to happen. Again, if you think about the reflection principle, if I ask what's the probability that m of t is bigger than or equal to m. So if I draw a path here and I want it to end above m, okay, so let's take this path, take one of these paths. If you want it to end above m and you do its reflection, you want the maximum to be above m. So let me say it this way. There are two ways the maximum can be above m. One way is that your path got above m and it stayed there, and at the final time it's above m. And the other way is that at some point it got above m and then it came back below. If you take the path that got above m and came back below, and do its reflection, it'll end above m as well. So what you want to do is you want to take the ones that are above m at the final time, and you want to double it. Once because you've got paths that really are above m at the final time, and once because you've got paths that got above m and then fell back below, but their reflections are above m. And so you do the doubling of that, and that's the formula that you're seeing here. Right? If you now take the derivative of this with respect to m, you're going to come to this formula, and it says the density for m is just twice the density for w on half the line. One of the uses of that is that you can compute things called first passage time, or densities. Is the time tau sub m. It's the first w gets to level m. Well, the probability that the first time w gets to level m is before t is the probability that the maximum at time t is bigger than or equal to m, right? The max is bigger than or equal to m if and only if the first time you got to m was before t. And so then you can take the derivative of this with respect to t. Plug into this formula here. Again, I won't do the calculations. You just follow your nose through the calculations and you'll get this m over t root 2 pi t e to the minus m squared over 2t. This is for t's bigger than or equal to 0. We're used to looking at formulas like this and thinking of them as densities in the m variable. This is a density in the t variable. Right? It's the first time that you get to level m, it's a density in the t variable. What happens on job interviews is that you get incorrect questions. So here's a typical incorrect job interview question. Suppose you have a geometric Brownian motion and the interest rate is 0. And we'll define S star of t to be the max of the geometric Brownian motion. And get some question like, what's the probability? We're working here under the risk neutral measure, and S is a martingale under the risk neutral measure. What's the probability that the maximum of the Brownian motion at time t is bigger than or equal to m? And what they're thinking is well, there are two ways you can be bigger than m. One way is you end above m, and the other way is that you were above m, but then you came below. And you take this path that was above m and came below, and you reflect it, and you'll get the other path. So you should count the other paths twice. And maybe this will work because S is a martingale, and it doesn't work. Okay, it works for Brownian motion, but that's it. So you cannot use, it's not equal to 2 times the probability that S of t is bigger than or equal to m. Okay, it doesn't work for martingales, it works for Brownian motion. Let's think about S of t. So it's S of 0 exponential sigma w tilde of t minus 1/2 sigma squared t, which I could write as S of 0 exponential sigma w tilde of t minus sigma over 2t, and let me call this w hat of t. And then let me define hat of t to be the maximum of w hat. of u 0 less than or equal to u less than or equal to t. And then the maximum stock price is S of 0 exponential sigma m hat of t. The stock price is S of 0 exponential sigma w hat of t. But now you can see the problem. W hat is not a Brownian motion. It's a Brownian motion with a negative drift, right? Right? This is not symmetric. So it's tending to go down. And so this argument that we used here is not going to work because of the asymmetry in W hat. So we do see that ST is bigger than or equal to M if and only if, so this is bigger than or equal to M if and only S of 0 exponential sigma M hat of T is bigger than or equal to M, which means that M over S of 0 log 1 over sigma, I guess. M hat of T is bigger than or equal to this. So we are interested in computing probabilities that M hat is bigger than something. Our problem is that the M hat is not a Brownian motion. Right? So how do we compute let me call this M hat. The P tilde probability that the process M hat of T is bigger than or equal to little m hat when W hat is a Brownian motion with drift. W hat of T is equal to W tilde of T. This minus sigma over 2 is a nuisance. I'm going to call it plus alpha T. In this example, alpha is minus sigma over 2, but I'm going to show you how to compute this no matter what the alpha is. And then we'll quit. Because there's a trick here that's worth knowing. And you can kind of guess what the trick is going to be. W hat is not a Brownian motion. It's a Brownian motion with drift, but we could change the measure and make it be a Brownian motion. So let's create a measure. So change to a measure P hat by saying the Radon-Nikodym derivative of P hat with respect to P tilde. Now we want to make this be a Brownian motion, so we should take e to the minus alpha W tilde of T minus 1/2 T squared, right? That'll make W hat be a Brownian motion. I'll call this Z of T. I would also like to write it in terms of W hat, e to the minus alpha, and W tilde is W hat, oh, I'm sorry, alpha squared T. W tilde is W hat minus alpha T. And so this is e to the minus alpha W hat of T. Here I have a plus alpha squared T and then a minus 1/2 alpha squared T. So I have plus 1/2 alpha squared T. I can write this Radon-Nikodym derivative process Z either in terms of W tilde or W hat. Here's Kirsanov's theorem with it in terms of W tilde, and then I've used the formula that relates W tilde and W hat and rewritten it in terms of W hat. So what are we interested in? Well, I'd like to do this joint density again, and we can. I'd like to compute the P tilde probability that M hat of T is less than or equal to some number, little m hat, and W hat of T is less than or equal to some number, little w hat. when I'm working under P tilde, W hat is not a Brownian motion, right? When I'm working under P tilde, W hat is a Brownian motion with drift. I'll write that as an expected value of an indicator. M hat of T is less than or equal to little m hat, W hat of T. I don't know why my little t's became capital T's. Let's switch them back just so we're consistent. Is less than or equal to little w hat and now I want to change here. So I would like to write this as E hat, but which way is our measure change going here? Right, so when you have P tilde, you use the measure change, you multiply by Z to go to P hat. I was somehow expecting to divide by Z. Well, that's obvious. Oh, yeah, that's right. Right. What does the formula say? It says that if you're computing the E hat expectation of something, you multiply by Z and compute the E tilde expectation. And that's the way the Radon-Nikodym formula goes. If I replace, so if I'm going the other way here, right, I have an E tilde expectation, and I want to write it in terms of an E hat expectation, I need to divide by Z. What you can do here in this formula is you can take X, take Y to be X over Z. Right, take a random variable X and write Y as X over Z. And then you see that if you've got E tilde of a random variable and you want to compute its hat expectation, you have to divide by Z. We're going backwards from the way in which we usually go. And so I have to put here 1 over Z of T indicator. And then what Z hat is, a Z of T is. Here's Z, but I have 1 over Z. So this is E to the alpha W hat of T minus 1/2 alpha squared T times this indicator. What have I accomplished? Well, I am now looking at W hat under P hat, and under P hat, W hat is a Brownian motion. So W hat is a P hat Brownian motion. And M hat is its maximum. And for Brownian motions, I know the joint density of the Brownian motion and its maximum. For Brownian motions, I know the joint density of a Brownian motion and its maximum. And because these are now Brownian motions under this, I can actually do the calculation of this guy. It'll be a double integral. E to the alpha y minus 1/2 alpha squared T. So I'm putting y in for the Brownian motion variable. Now I have to think about where do I integrate. The Brownian motion variable goes from 0 to w hat, minus infinity to w hat. I'll put it on the outside. And the other variable goes from, well, m has to always be bigger than or equal to 0, and it goes to m hat. And then I put in this density to x minus y t 2 pi t e minus 2x minus y squared over 2t dx dy. All right, so this is probably worth taking 2 minutes and recapping what happened. I have an answer here. Before I show you that I've got an answer, let me show you what I did. So what's the story? I start knowing from the reflection principle the joint density of a Brownian motion and its maximum up to Brownian motion at time t and its maximum up to time t. I know what that joint density is. The problem that I have to solve in order to think about a geometric Brownian motion, the problem that I encounter is that in the geometric Brownian motion, the thing that shows up in the exponent is not a Brownian motion, but rather a Brownian motion with a drift term, something multiplying time. And so that poses for me, how do you deal with that? Suppose you have something that's not a Brownian motion because it has a drift term and its maximum. How do you find the joint density for those? And the answer is we are going to use Kirsanov in a clever way. And then the clever way is on this page, but it's hard to see it the first time. What is it that happened here? So let me take it from the top, the outline of what it is that happened. So as long as I'm working under the measure p tilde, w hat is not a Brownian motion. And I want to compute this joint distribution under the measure p tilde, under which w hat is not a Brownian motion. And what I'm going to do is I'm going to change this calculation to a problem computing under the measure p hat, for which w hat is a Brownian motion, and then I'm going to use the density that I already know. And how do I do the change of measure? Well, I'm going backwards from the way we usually do it. Usually, we're trying to compute some expected value under the new measure, and we convert it back to the old measure by multiplying by z. Here, we're starting under the old measure, p tilde, and we're going to the new measure, p hat, and so I have to divide by z. I write down exactly what z is, and I write it in terms of w hat, because when I get to this point, I know the density of the joint density of m hat and w hat, and so I can actually write down what this expectation is. Here it sits. And what I'm looking at here is the joint cumulative distribution function of m hat and w hat under p tilde, and so this is the joint density right here. This is the density under p tilde of m hat and w hat as functions of x in place of m hat and y in place of w hat. And you see that what your Kirsanov theorem is telling me is that you take the density that you have for Brownian motion and you adjust it. And the adjustment is really the 1 over z term. Time is out. That's a clever trick, and it allows us to take things that we know for Brownian motion and convert them to things for Brownian motions that have drift. And then in particular, it helps us to understand how to behave with geometric Brownian motions. And then I can go out and start pricing various exotic options using this joint density. But that's just a long, messy calculation, and we don't want to start that at this time of night, at this point in the mini semester. Let me pause here and see if there are any final questions. You'll see all of this in the chapter on exotic options. Again, this is not something that's going to be on the final exam. If you find yourself in life working with exotic options, I'd like for you to know that it's there. And we also wanted to talk about the picture that was on the front of the book before the class was over. So now you know what that picture is about. Okay, so I will, unless you come back for this second half of this lecture again tomorrow, then here in Pittsburgh, I will see everybody on Friday afternoon. everybody who's interested in coming, and we'll spend as much time as necessary to make sure all of your questions are asked and answered before the final exam.